कल भी है एक से दिखाई देती है वेडनेसडे भी हम रेस्पॉन्स
Okay, so in the last class we have started talking about Lower flow or peaking flow or Stokes flow. Regarding your tutorials, so we'll have one from 2 to 3 on Tuesdays and another from 1 to 2 on Wednesdays. I saw in the request sheet that the sheet that Shyam had shared with you guys, most of you had agreed for one of the 2 days. Let me know if, but there was still few entries which were blank. So let me know if none of these times work for you, then I can plan for a third time. But for the time being, I'm assuming that everyone is available on either Tuesday 2 to 3 or Wednesday 1 to 2. Okay? And this is the room in which we are going to have the tutorial. LS623, the one that was allotted to us. For Tuesday, we'll use the same. For Wednesday, we'll use LS1 to 2. Sorry, LS5 to 7 from 1 to 2. Okay? Everyone with me? Yes. One more announcement. Today I won't be available for the tube. I'm planning to have today, I'm shifting today's tube to tomorrow, 6 to 7. Same room, LH517.
6 to 7 p.m.
Yeah.
Sir, we have a test schedule.
Internship.
I will check and let you.
Okay, let me know. You can move. There is some personal thing for which I am taking afternoon off. Anyway, so guys, please settle down. So in the last class we had started talking about Stokes flow. We are going to be discussing particle suspension, particles which are not undergoing Brownian motion, and for the purpose of this class will mostly be neglecting particle surface forces, or we will not be talking about it. And I'll let you know where that assumption may not work, under what conditions this assumption may not work. Alright, Stokes flow or peaking flow or low ensemble flow, your del V by del T term is 0 and V dot del V term is 0. So inertia and acceleration, both those terms are set to 0 at low velocity. So original equation, now this Stokes equation, along with continuity, there are 2 variables there, velocity and pressure. Okay, so you need 2 equations. But there are actually 4 variables there. If you think of velocity as a 3-dimensional quantity, a vector, 3 variables there and pressure, so and you have 4 equations. Now this Stokes equation is again a vector equation, which will have 3 functions. Alright, you can non-dimensionalize this equation. So left hand side can be non-dimensionalized with characteristic velocity. So here I am using capital U. जब Strabon number का discussion है, there I am denoting characteristic velocity with UC. Characteristic length with LC. Here I am just saying LU. And when I am non-dimensionalizing it and I am getting Reynolds number on the left hand side, you need to realize here, note here that when I am writing my left hand side, non-dimensionalizing my left hand side by rho u square by L, I am essentially writing my time as L by u, or my characteristic time as characteristic length by characteristic velocity. वो assume करके मैं Reynolds number left hand side में आ गया, when Reynolds number is small, I neglect this and only worry about the right hand side. Okay? All with me? Now I was asking, and once we have this linear equation, so left hand side is viscous flow, right hand side is potential flow. So you can derive Bernoulli equation from the potential flow equation on the right hand side. In Bernoulli equation, you neglect viscosity. You assume your fluid to be in this way. Some examples of Reynolds number flow. Again, the Navier-Stokes equation or Stokes equation, these equations are only and only valid for the fluid. They do not, when we'll, I mean, right now the confusion is not there, but once we start talking about suspensions where we have particles suspended in the fluid, we have to realize that Stokes equation or Navier-Stokes equation is only and only for the fluid, not for the particle phase. Rigid particles do not deform. Fluid flow problem are by definition for deforming entities. The difference between the fluid or a rigid particle is the same. Your fluid can deform, rigid particles no. Okay, so when we move from Navier-Stokes equation to Stokes equation, when we neglected the inertial term and W by del T, we are left with this linear term, linear equation, which has some beautiful characteristics. It's going to be instantaneous since there is no dependence on the time now. Linearity is there, so you can use a lot of skills that you have with linear differential equations. And then reversibility, and we'll go over some examples for showing the impact of characteristics of Stokes. Guys, I'll really appreciate if you don't talk during the class. I'll ask you to leave in case I find somebody. Okay. Thank you. Bye. So we are so del U by del T is negligible when the Reynolds number is small. The flow responds immediately to forces, no acceleration. So when my particle is settling, when my particle is settling, I'm assuming, let's say when mg is acting on the particle is settling, and if I turn off g, Stokes equation is saying the particle will stop moving almost immediately, almost instantaneously. The velocity can still depend on time if my g and g wala sirf example hai. I mean, of course, the particle is moving because of n number of other things. So your velocity could still be a function of time when external forces are time dependent, but not on time as an independent variable. I mean, your velocity would not be changing as a function of time without any change in any external forces. Ladies, you are late by a minute. Today I am allowing from tomorrow. I am going to ask you to write my name there, and then you can just So An obvious question that you would ask is, how instantaneous is this instantaneous change in velocity? If my particle is at zero velocity now and when I let it settle, it's at the terminal velocity, how much time does it take, or how instantaneous is it in the time scales of this problem? All right. Again, as I mentioned earlier, for a dimensional quantity like time, I cannot say it's small or large. There is no small time or there is no large time. Any dimensional quantity cannot be small or large. I hope that point was clear.
Yes.
Yes.
For non-dimensional quantities, you can say it's a small quantity or it's a large quantity. I'm making 100 rupees a month. Is that a small salary or a large salary? How is it small?
We need a reference.
As a kid, when I used to get 100 rupees a month, it was awesome.
We need a reference.
So, you can only be scaling if I'm only comparing myself with Elon Musk. $1 million, few $100 million a month is still not enough. I mean, still a small salary. So again, I mean, for a dimensional quantity, you cannot. Am I tall or am I short? I'm very short compared to a giraffe. I'm very tall compared to a cockroach here. But I mean, again, typically when we say somebody's tall or somebody's short, we are sort of non-dimensionalizing the height of the person with the average heights. Okay? So only non-dimensional quantities can be small or large. Okay, so when I'm saying instantaneous, almost immediately, it doesn't make sense when as a dimensional quantity, how small is this almost immediate transition of velocity. So now I'm just trying to show you how you can estimate the time scales associated with this change in velocity. I've rewritten Navier-Stokes equation. And here, instead of writing my time, non-dimensional time or non-dimensionalizing my time with L by U, instead of that, I'm saying, let's say there is a characteristic time, tau c, and I'm non-dimensionalizing my time with tau c. And once I do that, this entire equation will have a term given by LC by UC tau c. पहले मैंने tau c को assume किया था, the characteristic time in which I am interested in, I had assumed this to be equal to L by U. So ये 1 हो गया था, and all we were left was this equation, and then we said that Reynolds number is much smaller than 1, so भूल जाओ left hand side को, and all you need to worry about is right hand side. ठीक है? Now I'm saying I'm interested in finding out at what times do we I'm going to reach this conclusion of neglecting du by dt, or is there any time for which du by dt could be important? Is there a time for which acceleration term could be important? I mean, we know zero velocity and finite velocity. Changes are taking place. How fast are they? So now, let's say I do not know how fast it is, so I'm calling this time to be I'm representing this time to be a characteristic time of tau c. So tau c से denote किया मैंने non-dimensionalize किया t को. I wrote t as t dash multiplied by tau c. Okay. So once I use tau c for non-dimensionalizing my time, we end up with tau number. Okay. And Now, my Reynolds number is still much less than 1. वो problem statement है, Reynolds number is much less than 1. So you can neglect this term. You can also neglect this term if Strahul number times Reynolds number
It's less.
is still much less than 1. There are really 3 entities in this non-dimensional world. Much less than 1, 1, and much larger than 1. So Reynolds number times Strahul number, when can I neglect my del U by del T term? When Reynolds number times Strahul number is much less than 1. My Reynolds number is much less than 1. So when are we going to violate this?
When Strahul number much greater.
Sorry?
When
When Strahul number is much greater than 1. And what does that mean when my Strahul number is given by LC by UC?
tau c is very small.
So at these characteristic times, for this problem you can imagine, again in this problem there is only one length scale that you can think of with this particle settling down, size of the particle. This is an infinite pool of fluid. So कोई और length scale नहीं है associated with this fluid. So this particle size is one length scale, its own velocity or its terminal velocity is another length scale. So Strahul number is going to be much larger than 1, or this term is going to be important only and only for time scales much less than L by U or LC by UC, where L is the size of the particle, U is its terminal velocity. So L by U is essentially the time it takes for this particle to cover a distance equal to its own size. That itna time, and your tau c has to be much smaller than that. So जितना ये time है that this particle is taking to cover a distance equal to its own size, for time scales much smaller than that, this del U by del T term is going to be important. Okay, which for the purpose of most problems is you can neglect, or these are time scales for which you may not be interested in. Of course you will be interested in those time scales when even that transition is important for you, or you are interested in for your problem, you are interested in studying that dynamics of 0 to whatever velocity you are moving to. Alright, so when you are interested in those time scales, worry about it, include the del U by del T term. When you are not, you can forget. Alright. One homework assignment, calculate the time scale over which a rigid spherical particle of diameter 10 micron will reach terminal velocity in water. So water की सारी properties तुम्हें पता है. Assume the specific gravity of the particle to be 1.1. So I'm essentially asking you to get an idea of the time scale associated with a particle of this size to reach its terminal velocity. Okay, later on, when we will be looking at finite Reynolds number problem, or from your fluid mechanics course, you can look at similar problem and ask for how much time will it take for, let's say, a water droplet settling from clouds. How much time a water droplet settling from cloud will take, just to get an idea of the dynamics in Stokes' law compared to finite Reynolds number. Okay, so that was instantaneous. Then another characteristic of Stokes' law is the linearity of the equation. Okay, there is no u square term now. The second term on the left hand side was u dot del u quadratic figure. There's no u square term now in this equation. Before we jump into the details, I just want you guys to take a step back, and you guys have studied laminar flow in the past. Like the first problem was that pipe flow. So is laminar flow and Stokes flow same? Anyone at the back? Is laminar flow and Stokes flow same? Yes. Yeah, differences and which?
Laminar flow can have large Reynolds number.
Laminar flow can have large Reynolds number.
Yes.
Okay. How is laminar flow different from turbulent flow?
A lack of molecules or all streamlines
All streamlines?
being parallel, not intermixed. Streamlines are intermixed.
So what does finite? A more proper definition for laminar flow is it's applicable even for finite Reynolds. Okay, qualitatively, can there be any difference between laminar flow and Stokes flow?
Stokes flow can be understood as a specific part of laminar flow where we are neglecting the viscous forces. Sorry, the
Laminar flow meaning?
inertial forces. In laminar flow, both the inertial and viscous forces are important, but in low Reynolds number flow, we are neglecting the inertial.
We are completely neglecting the inertial flow. So we are in Stokes flow, I am neglecting the entire left hand side. For laminar flow, not necessarily. Your left hand side is important. It's still not turbulent flow, but your left hand side is important. Yes. You are going to see that if you solve for pipe flow, I am injecting water in my pipe, and under the laminar flow condition, you found this Hagen-Poiseuille equation to be satisfying the flow dynamics inside the pipe. That was using Navier-Stokes equation. If you were to solve this problem for Stokes flow, assuming that there is low Reynolds number flow inside the pipe, you are going to get the same result. And the reason for that is equations अलग हैं, फिर भी same result आता है.
Can you repeat the question?
I'm saying Stokes flow or laminar flow for something like a pipe, same result आएगा तुम्हारा, even though you are using different governing equations. And the reason for that is one is for pipe flow we solved for steady state flow, so del u by del t term went to 0. The second thing is the second term on the left hand side is u dot del u. So u dot del u अपना gradient of velocity है, u is the direction of velocity. So u dot del u, since the direction in a pipe flow, the gradient in velocity is in this direction, is in the radial direction, whereas flow direction is your axial direction. The dot product goes to 0. Unidirectional flow here, as a result of which the second term also goes to 0. So although you started with Navier-Stokes equation. There, due to the direction of the flow, due to the unidirectional nature of the flow, the velocity, the final solution comes out to be same. If this was a pipe flow like this, laminar flow solution and Stokes flow solution are not going to be same. Anyway, sticking to the linearity of Stokes flow, so we are taking care of, we are neglecting the non-linear term, the u dot del u term. Let's look at some of the advantages that linearity of this flow brings. So, guys, please, one of you white shirt and black t-shirt, either separate or one of you leave the room. So, let's look at some. So let's look at how this linearity of Stokes flow can help in simplifying some of the problems, or in fact can help us in solving some of the problem without actually solving the differential equation. So let's look at this spherical particle in simple shear flow at some streamline in the simple shear flow. And I ask you whether this particle is going to go up or down. Is there a possibility of a lift force acting on this problem, on this particle? From this problem statement, you may not be able to tell कि lift force होगी या नहीं. Now let's look at the linearity. Let's use the linearity of Stokes flow. I'm giving you it's Stokes flow, simple shear flow. The particle is at some streamline in simple shear flow. Tell me whether there is going to be a lift force acting on the particle or not. Here directly you may not be able to tell, but let's use the linearity of Stokes flow equation to divide this problem, more complicated problem, into simpler problems. So here your particle was free to rotate in simple shear flow. Here the first set of problem is rotating sphere in stationary fluid where the fluid is stationary at infinity. Second is particle in uniform flow. So here the particle was at some streamline, essentially whatever the velocity of that streamline was. I'm saying that the particle is in that uniform flow. And the third is, now the particle is not rotating and it's in simple shear flow centered at the center of the simple shear flow. So I brought that particle here. नीचे ले आया उस particle को, rotation उसकी बंद कर दी. Here you can tell there cannot be any lift force acting on this particle due to symmetry. If there is a lift force acting in this direction, equal and opposite lift force should be acting in the opposite direction. Same goes here. Spherical particle in uniform flow. Again, symmetry of the problem is such that there cannot be a lift force acting in this direction, or अगर इस direction है तो इस direction में क्यों? Third thing, again the same. Your particle is rotating in stagnant fluid. Again, if there is a lift force in this direction, there should be an equal and opposite lift force in the other direction. So I've essentially divided this more complicated problem into simpler problems and from there concluded there cannot be any lift force acting on this spherical particle in simple shear flow at some streamline. And the only reason we are able to do this is because of the linearity of Stokes. So if I'm blowing wind on this particle and around this particle, and I'm also punching or applying any external force, if this particle or if this fluid, if this problem was a Stokes flow problem, then I can solve two different problems. One is where I'm just blowing wind around this particle and calculate force, torque or dynamics of this particle. Another is where I'm applying this external force on the particle and again calculate force, torque or dynamics of the particle. And summation of both these solutions will be the solution where I'm blowing air and applying the force. And that is again only and only possible because of the linearity of Stokes. This would not have been the case if this problem was non-linear. Any examples? Non-linearity में क्या? Any questions, guys? I think you had one.
No, I was just asking if we are assuming in the first figure that our rotating sphere is at the center of it.
The rotating sphere
Is at the center of our basically.
it's infinite domain, so center is really
As in at the intersection of our two this. And
The
like
point-
in the third figure, we
Yes.
are no, in the third.
Fourth.
We are assuming it to be at the center of our.
Yeah, so here it's again uniform flow. Uniform flow is ऊपर नीचे हो सकता है लेकिन it doesn't matter. It's the same velocity. And the velocity that I'm using is the velocity of the streamline.
So in a linear breakdown of the third term, so would there be lift or no lift? Would that not depend on like where the particle is in terms of whether it is away from the center or not? Because in our first, the original figure, it is not at the center. But when we do that linear breakdown, we have presumed it to be at the center.
हाँ यहाँ पे सेंटर में है इसलिए मेरे लिए आसान है बोलना कि नहीं कोई लिफ्ट नहीं होगा इस पे
तो ऊपर या नीचे हुआ तो मतलब लिफ्ट होगा.
नहीं ये तीनों का I mean in तीनों में we are seeing that there is no lift on the particle and summation of these three problems is the problem on the left hand side. So now from there I have concluded
So what
कि
if
पार्टिकल ऊपर भी होता ऊपर है तो भी लिफ्ट नहीं है उस पर. Am I making sense?
So can you please?
So without actually solving any differential equation here or without solving Stokes equation here, just by using the linearity of the problem, I'm able to claim जो इतना obvious नहीं था for the first left hand side problem, the given problem इतना obvious नहीं था कि यहाँ पे force लग सकता है या नहीं. By dividing this problem into three simpler problems where based on the symmetry of the problems I can say there cannot be any lift acting. उससे I am concluding there is no lift acting in this problem. Somebody was asking something. Okay. Make sense?
Yes.
The third characteristic of again Stokes equation is reversible. And guys, these are things जो सारी linear equations के लिए तुमने already देखा हुआ है. I mean, there is nothing special about Stokes equation. It's just that some of the like a feature like this is something that will not be obvious for you. So I'm asking. I have two cones here. In fact, same cone that I've rotated by 180 degrees. So a cone in uniform flow, a stationary cone in uniform flow, I'm holding it in uniform flow. I'm asking what is the drag force acting on this part. Then again a stationary cone, I'm holding it in uniform flow in this geometry, and I'm again asking what is the drag force acting on this part. Let's say the drag force is dA and dB. And the question that I'm asking is, how is dA related to dV? dA बड़ा होगा या dV बड़ा होगा? वहाँ से wind blow हो रहा है. I'm holding this bottle like this. I'm asking what is the drag force acting on this bottle, and then I'm holding the bottle like this. हवा वहीं से आ रही है. I'm asking what is the drag force acting on this bottle.
DA should be greater than DB.
dA should be greater than dV और क्यों? Well, वैसे surface area same है, मतलब same bottle है. ऐसे लिया और ऐसे लिया.
The angle of the surface
I don't think in terms of momentum. Momentum के साथ components directly stop हो जाएगा उसमें self component.
Any other possibilities? Same क्यों हुआ?
क्रॉस सेक्शनल एरिया सेम लग रहा है.
Cross sectional area same है वैसे. And I know some things that you have read in fluid mechanics 101
Sir,
वो suggest करेंगे same, लेकिन
Sir, is that as effect coming just to
assume कि ये smooth edges हैं, मतलब ऐसा सारे differential equations सब कुछ valid edges. Interestingly, and of course for a car you know कि आगे से car I mean, so we have Maruti vans जो बिल्कुल flat होती हैं, उसमें your area is sort of same. Otherwise, typically in a car from in the beginning you have a lower height and then that increases. और पीछे से गाड़ियाँ flat होती हैं फिर से, at least most SUVs. And that is done to reduce the drag acting on them when they are running on the road. Okay? But that is not Stokes law. They are typically not running on the road in Stokes law. Here, interestingly, the drag force acting on these two particles is going to be same, absolutely same. And the only reason for that is the linearity of Stokes law. So, now again without solving, let's try to see क्यों same है. Here are the two differential equations that we have to solve to drag force कैसे निकालते हैं वैसे typically for the spherical particle that was settling in the fluid. How were you calculating the drag force acting on it? How did you calculate the drag force acting on it? You essentially, yeah. The particle viscous fluid में drop हो रहा है. I'm asking the drag force acting on this particle. How did you solve for it? You have done this exercise and you
फोर्स बैलेंस कर लेते हैं.
force balance. Force balance जब किया था तुमने, you balance the gravitational and buoyant force with the drag force acting. But drag force का expression जो था, that you derived. And the way you do it is, you essentially solve for Stokes equation around this particle. From the Stokes equation, you solve for velocity field around the particle. From the velocity field, you can calculate the gradient of velocity on the surface of the particle, and from there you can get the stress and integrate the stress over the area. Shall I revise? So you are solving Stokes law. Stokes law solve करके क्या मिल जाएगा, या Navier-Stokes solve करके क्या मिल जाएगा? Velocity field. How is the velocity changing as a function of position? So for the surface of the particle, you can calculate how the velocity is changing around this particle. So to make gradient of velocity मिल जाएगा. Using Newton's law of viscosity, you can tell what will be the stress acting on the surface of the particle. And if you integrate the stress on the surface of the particle, stress into area क्या होता है? Force. All right, this is how you did that exercise. So again, for this problem, one can solve for velocity field by solving for Stokes equation. You need boundary conditions to solve this. The boundary conditions are u equal to 0 on the surface and u equal to u far away from the surface. Particle stationary रखा है, ये bottle मैंने stationary रखी. Okay, so on the surface of this, the velocity is 0, and far away from it, velocity is u. Second में क्या कर दिया मैंने? So I was changing this, I was rotating this particle by 180. Now let's say I keep the particle same. Instead of blowing air or fluid from that direction, I'm blowing fluid from that direction. All I've changed is velocity direction has changed, nothing else. Stokes equation remains the same. My surface remains the same. So boundary conditions remain the same. On the surface, it's still u equal to 0 and u is equal to minus u far away. Our velocity ये है, earlier it was this. Other than that, governing equations are same. Boundary conditions are same. So solution क्या होगा? In fact, now you can say that u is equal to minus u is equal to minus u far away, and u equal to minus 0, on the surface. Governing equations are same, so solution is going to be equal and opposite. So जो भी velocity field पहले था, the velocity field for the second problem is going to be same except negative values only. And now if I'm going to integrate the forces acting on this particle, I'm going to get the same result except the direction is going to be opposite. Am I making sense? So drag acting on these particles is same, and the only reason this is happening is because of low Reynolds number. If I'm driving two cars of these shapes, the force acting on the mileage of this car is going to be better than that. The drag force acting on that is going to be lower than that. Not in the case of Stokes law. Any questions? Not in the case of this linear flow.
So can we say that in the orientation of the body doesn't matter in Stokes flow?
Well, नहीं, मैं ये नहीं कहूँगा. This same. No sir. मैं body condition u equal to 0, मतलब u equal to 0 on the surface is no longer same. The moment I'm doing this. Here I'm doing this, flow from this side, flow from this side, it's same. गाड़ी अगर चलाऊंगा मैं तो ऐसे ड्रैग ज़्यादा लगेगा, ऐसे कम लगेगा compared to ऐसे. But for this particle, if I'm going to move this particle like this in Stokes flow, it's same. Finite Reynolds number, high Reynolds number, no, same. Stokes flow, same.
Sir, what will the streamline look like in both conditions?
Exactly same. Exactly same. Direction अलग हो सकती है. Questions, guys? Please ask something, because I'll be basing a lot of our future discussion assuming कि we understood these basic features of Stokes law.
Will the streamline near the surface look like it will be grating on the surface? Like directly touching the surface.
Yeah, I mean, fluid is there in touch with the surface. No slip bonding condition is there touch with, on the surface.
So if this is the case,
मतलब नो स्लिप बॉन्डिंग कंडीशन अगर फाइनाइट रेनॉल्ड्स नंबर होता तो भी नो स्लिप बॉन्डिंग कंडीशन नो स्लिप बॉन्डिंग कंडीशन या
talked earlier about the cars example, right? Cars on the road. So why, like if this is the case, if overall projected area is only the thing that matters.
नहीं मैं ये प्रोजेक्टेड एरिया इज नॉट द ओनली थिंग दैट मैटर्स
We lost you.
प्रोजेक्टेड एरिया वाली चीज नहीं है मतलब ऐसा नहीं है कि आई एम नॉट सेइंग कि द सेम पार्टिकल इफ आई गिव यू अ सिलेंडर विद दिस प्रोजेक्टेड एरिया इट्स नॉट द सेम यहाँ पे वो प्रोजेक्टेड एरिया वाली चीज तुम यूज करते हो फाइनाइट रेनॉल्ड्स नंबर आई मीन इंजीनियरिंग प्रॉब्लम में टू गेट एन एस्टिमेट यहाँ पे मैं कह रहा हूँ कि इट्स एग्जैक्टली एंड मतलब मैथमेटिकली दिस इज कमिंग गोइंग टू कम आउट टू बी सेम solve this differential equation and you are going to get the same result, and the reason I'm telling you without solving it I'm able to say this because it's a linear equation and the only thing that is changing is the direction of the flow, which is not the case for finite Reynolds number where I have u dot del u term. तो गाड़ी के केस में नहीं है ये applicable बिल्कुल भी because you are running your car at finite Reynolds number or at high Reynolds number. So u dot del u is going to be important there. And I'm not claiming that this is same because the projected area is same. Not at all. बिल्कुल नहीं. Are we on the same page, guys?
Yes, sir.
Solution of this problem is going to be whatever u velocity field or pressure field is going to be there, and for this it's going to be exactly same in opposite direction.
So what is u and t?
Velocity field and pressure field, मतलब ये दो ही variable हैं. Navier-Stokes or Stokes equation and continuity equation, two equations, two variables. So general statement for reversibility, if u p is the solution of the Stokes equation satisfying appropriate no-slip boundary condition on a solid surface, then minus q comma minus p is a solution of Stokes equation with all external forces and motion of all the boundaries reversed. जो यहाँ पे motion of the fluid I have reversed. But in general, when I am changing all my external forces and boundary conditions, if they are reversed, the solution is going to be exactly same. Just u is replaced by minus u and p is replaced by minus p. Are we on the same page, guys?
Yes, sir. Which is
This would not be true for a non-linear equation like Navier-Stokes. ठीक है? अब तुमने एक क्वेश्चन पूछा था कि for any orientation would it be true? This and this, it's not going to be true. This is a fluid problem, and we are going to see how this force and this force are related to each other. These are cubes here. So this and this is not same. For this shape, we are going to see ki same iron. But anyway, we are going to see this mathematically. We are going to show this. Alright, guys. So see you tomorrow. We are not meeting for the tutorial today. We'll be meeting either tomorrow at 6 p.m. Tuesday group will be meeting tomorrow at 6 p.m. or if you have an internship test by OCS, then we may shift it. And guys, please try to be on time in the next